Okay, so let's look at these reactions in totality, right? Now that you all know the equations for delta H and delta S and all that stuff, now this chart hopefully makes sense. So the first thing that you want to do for reaction X is write the expression for the equilibrium constant. And they even tell you there's two different ways that you can do equilibrium in reaction. You can base it upon concentration or you can base it upon pressure. So guess which one they want you to use? Pressure. So when you look at this reaction, you can only deal with things that potentially you can measure as pressure. So do you think you can measure the pressure of solid carbon?
No. Solid carbon?
No.
I didn't.
Okay?
I learned it. So.
Now, here's the other thing that's important. Notice here they listed water as a gas, not as a liquid. So what that means is this would be happening under higher temperatures. Okay, so it's just going to be the pressure of the carbon monoxide times the pressure of the hydrogen gas divided by the pressure of the H2O. That's it. Okay? Now, Will Stanley, why is nothing squared or cubed?
There's no coefficient.
There's no coefficient. If one of these had been, like if there had been a coefficient in one, of 2 in front of one of those, we would have squared it. So literally, that's all you have to do. Okay? That's it. You don't have to calculate anything. You're just writing the expression. That's it. Oh, not make it complicated. Now, look at the totality. For reaction X with equilibrium constant pressure, increase, decrease, or remain the same if the temperature rises above 298 Kelvin. So, here's the story. Notice that up at the top, all these are delta H knots, delta S knots, delta G knots. What does that mean?
Standard conditions 25.
They're under standard conditions of 25 degrees Celsius. Look at this combination of a positive delta H and a positive delta S. Two things are both positive. Okay? Temperature dependent. Temperature dependent upon high temperatures, temperature dependent upon low temperatures.
Above.
Above, because you have both things. OB, which one is driving it towards spontaneity? The entropy term or the enthalpy term?
I do not need you to call me, okay? I did not come here to get chastised.
I'm not chastising you. I'm asking you a question.
I think it's entropy.
Why?
Pass to the next.
Because Mother Nature likes a hot mess.
Mother Nature likes a hot mess.
And that's a
I don't
mess.
identify.
Entropy is a mess.
Entropy, so you have a positive delta S, which means that the entropy is increasing. Okay? Now, remember this.
I need to make
They could have asked you to predict the sign of delta S even beforehand. And here's why. How many moles of gaseous product do you have?
2.
2. How many moles of gaseous reactant do you have?
1.
So anytime you increase the moles of gaseous product, because gases have a lot more entropy than solids or liquid do, that's consistent with the idea that we should have a positive delta S. Now, you have a positive delta H. Natalie, you have a positive delta H. Is it endothermic or exothermic?
I got that one. Endothermic.
Endothermic.
Bingo.
So is heat being put into the system or is heat being taken out?
Put in.
Heat is being put in. You have a positive delta H. This is going to be an important part of the story. Okay? So it's endothermic. Okay? So we're going to raise that temperature up above a certain value. Heat's going into the system. So when you get to that question B, it says, hey, what's going to happen to the value of Kp? So this is where you have to look at this mathematically. If you increase the concentrations, if it shifts to the right by adding heat, Kp is going to get bigger because you're going to shift to the carbon monoxide and hydrogen production. If you add heat and it shifts to the left, the carbon monoxide and hydrogen are decreased, the water is going to increase. So this is what you have to figure out. Since it's endothermic, if I add heat to it, which way is it going to shift? Is it going to shift to the right or is it going to shift to the left? I don't know.
To the right. Because
Why?
they're getting more energy.
Yes, because
Okay.
because it's endothermic, energy is a reactant. Because you have to add energy to it. If it was exothermic, energy would show up as a product. So since it's endothermic, it would be no different than increasing the concentration of water or increasing the amount of carbon. So don't be afraid to look at what's actually happening. Physically, this is what you're doing. You're taking carbon, solid, otherwise known as a piece of charcoal, and you are adding hot water to it. That's what you're doing. Okay, you're adding hot water to it. And what you would get is carbon monoxide gas and hydrogen. Okay? That's what would happen. That's what you would get out of it. So you'd get a poisonous gas and hydrogen. That's what you'd get out of the system. Now, at room temperature, is this a spontaneous reaction?
No.
Why not?
Delta G is positive.
You have a positive delta G. So even if you tried this at room temperature, this is one of the things I didn't do in the lab today. I didn't give you all a piece of charcoal and some steam and go, hey, let's see if we get a reaction. The only thing you'd end up with is wet charcoal. Okay? That's it. You would have soggy charcoal. Yeah, you would. Because this reaction wouldn't take place. Now, if it did take place, what would you physically observe happening if this reaction actually took place?
Bubbles.
Huh?
Bubbles.
Maybe?
Yes. You want to be able to breathe.
No. What would happen? You're reacting this with carbon.
The charcoal would go away.
The charcoal would go away
It's true.
because charcoal would turn into carbon monoxide.
Oh,
Okay.
Right.
Because all of the gases, the hydrogen gas, the carbon monoxide gas in the water, they're all clear. So if this reaction did take place, the easiest way to see if it happened, the chunk of carbon would disappear over a period of time. Okay? That's what you would see. All right, so that leads us to question C. So anyway, so on that answer, because of the fact that you're making more carbon monoxide and hydrogen, what's going to happen to the value of Kp? It's going to increase because heat is a reactant. So if you add that, it's like you're adding one of the reactants, and the reaction is going to shift, and you're going to make more product.
Wait, okay, so is that like because wait,
That's for myself.
okay, we're adding heat, but the you know what? I don't know what I'm talking about.
Oh.
I think I understand now.
I
Because-
barely did say anything, Natalie. No, you don't.
Because it's here. Okay, let me contrast this. If you burn gasoline, is that an exothermic or endothermic reaction?
You'd be giving off to be like
X.
right?
If you burn gasoline, is that an exothermic or endothermic reaction?
It'd be giving off heat to the exo, right?
The exothermic.
Yeah.
So burning of gas, heat shows up as a product side. Okay? That's exothermic. So if it's endothermic, heat shows up as a reactant. So since it's a reactant, if I increase anything on the reactant side, it's going to shift it over there. So it's going to shift it to make more product. Because it needs
Okay.
energy for the reaction to take place.
Okay, that makes sense.
Okay? All right? Cool. Okay. So on C, for reaction Y at 298, Kp greater than, less than, or equal to 1, justify your answer. So, what do you got?
I said less than 1 keeps on spontaneous.
Yeah. So, if you look at reaction Y, you have a delta G of 29 kilojoules per mole. And that's a positive number, right? So there's three things that fit together with spontaneous reactions. What's the sign of delta G?
Negative.
Negative delta G. What about your K values?
Small. Oh, big.
Spontaneous reactions, you have a K values bigger than 1.
Very big.
What about your E naught values?
Positive.
Positive. Okay? Those are going to be positive. So as soon as you see reaction Y, where delta G is a positive, delta is positive, that means the reaction isn't spontaneous.
This is gonna be less.
So K is going to be less than 1. If you had a negative value for delta G, then it would be spontaneous and K would be bigger than 1. Okay?
So it's just less than because it's positive?
Yep.
Okay.
Because you have a positive, you need to say, just don't, if you're on the test, just don't say, oh, it's less than 1 because delta G is positive. That's not a good answer. You want to say delta G is positive, so that indicates it's non-spontaneous. Therefore, K is less than 1. Okay? Just don't say because delta G is positive. You need to convey what that tells you. Okay? All right. So then you're on to question E. Following statement, true or false, justify your answer. Oh, no. Skip D. For reaction Y, which is larger, the total bond energy of the reactants or the total bond energy of the products?
Products, right?
Okay. So, remember, here's the rule. When you break bonds,
Oh.
no, you're good.
Oh.
When you break bonds, which way does energy flow? In. When you form bonds, energy is flowing out. So, for reaction Y,
So it's forming.
you have a positive delta H, which means it is endothermic, which means you took in more energy than you released energy. So what that means is that you had to take more energy into breaking the bonds, and this is the big energy one. So you had to break the bonds that held the carbon dioxide together and the hydrogen. So that input of energy on reaction Y to break those bonds was more than the energy that was released in the formation of the carbon monoxide and water. Okay? Does that make sense?
So the products as well.
So exactly. Okay. So if it had been exothermic, which it wasn't, if it had been exothermic, then what?
Then the reactants would have more.
Yeah, because you would have released more energy in the formation of bonds than you did in the breaking of the bonds. Okay?
How would we go about explaining? Can you explain that part one more time?
Yeah, so on D, all you'd have to say is that there's more bond energy. I want to abbreviate this in the products
Not necessarily. Which is false. That's not the same thing.
because, excuse me, on the reactants. Because you had to put more energy in to break bonds, than energy was released. That's energy in the formation of bonds.
Wait, so it's reactants, not products?
So if you look, so here's the story. So if you look at your options, okay, there's a total bond energy, the reactants, and the total bond energy of the products, which is greater. Okay? So because of the fact that it's endothermic, you had to put more energy into breaking the bonds in the reactants than you got in the energy made in the products. That's why it's endothermic. If it had been exothermic,
And we just know this based on looking at like G values. We can determine.
no,
Like,
that's based upon your delta H values. Your
based off of
enthalpy,
if it's endo or exo.
your delta H tells you if it's endo or exo. Delta G just tells you if it's spontaneous or not.
Yeah, I knew that. I don't know why I said that.
You
Okay.
said both, right?
So on E, is the following statement true or false? Justify your answer. On the basis of the data in the table, it can predict that reaction Y will occur more rapidly than reaction X will occur. Now, this is a bogus statement.
Not necessary.
Not necessarily.
Okay, here's why it's a bogus statement. Neither reaction is going to take place.
Yeah.
That's why it's a bogus statement.
Are they gonna do that to us?
I don't know. I was just irritated when I saw that question.
That's a good trick question. I like it.
Okay, so you could say it doesn't matter because neither reaction is going to take place. But what they were going for, let's assume that both of those had been negative values for the sake of argument. Let's say your delta G's had been negative values and both reactions took place. The value and magnitude of delta G does not reflect speed.
Well, yeah, because you said before, like, spontaneous doesn't mean it happens immediately.
Exactly. Okay? So the statement is false because your delta G values don't have anything to do with reaction rates. Okay, now let's consider reaction Z, if you're British or Canadian.
You wish you were
About
Canadian?
reaction.
Are you serious?
Not Canadian, but from Canada.
Bro.
We're
2/3 of your check.
we're African Canadian.
Okay,
Wait, are we gonna be doing the backside of this?
No.
paper?
Oh, yeah.
Alberta.
so
Polish.
So here's reaction Z, the mark of Zorro. So you just want, all you're trying to do is predict the sign of delta S. All you're trying to do. Positive, negative, or zero?
Negative.
Why negative?
Solid form.
2 moles of gas going into 1.
There's your option. That's how you want to express it.
Or X,
Okay.
where you flip X and Y. That's negative.
So you end up with 1 mole of gas, but you started with 2. So since you're decreasing the moles of gas, you've got to figure that your entropy is going to do what?
Go down.
Go down.
And you're forming a solid which locks it in place, which means it can have less microstates.
Can you Hess's law with energy? With,
Oh,
entropy?
absolutely.
You can?
You do with delta G, delta S, delta H.
Yeah, you'll find that it's right here.
So what'd you end up for your delta S? Positive, negative, zero?
We said negative.
Negative. Because of the fact that you only have 1 mole of gaseous reactant, but you had 2 moles of gaseous product.
And the solid's forming and it's locking those things in. And
If
there's
you
less
go with that,
microstates.
I would just talk about the gases.
Okay.
But you can talk about that. Now, we need to determine the value of delta H for the reaction.
Hesser.
So what can you do?
Hesser up.
Hesser up. Okay? So if you look, you can arrange those equations up above. This is another reason why I had to wait till we get to that point. So you can rearrange those equations at the top so that they add up to the bottom one. Now, in this situation, for example, what are some things that you want to get rid of?
We want to get rid of water.
You want to get rid of water.
Hydrogen gas.
You want to get rid of the hydrogen
Is
gas.
that it?
But you want carbon monoxide as a,
Reactant.
and you want carbon as a. So in this situation, do you actually really need to even flip anything?
No.
Just flip them around.
Yeah.
You're supposed to have negative.
Yeah.
Yeah, but I mean, as far as, that's what you got going. So if you do this, then you should get an overall delta H of
Negative 170.
negative 172. So now you have a negative delta H. So this is what I want you to think through at this point. So if you rearrange those equations up above, you can add them together. Okay, you've got to flip them, right? And you're going to get a negative 172, which is your value of delta H, right? So now you have a negative delta H. But what did you predict for your sign on part 1?
Negative.
So I've got a negative delta H and a negative delta S, which means that it is
Temperature.
temperature dependent.
Low temperature.
Is, oh, two negative people are like,
They bring it down.
bring you down, bro.
Don't bring me down, down. Okay, so it's a good song. So don't make me play it. So if this combination, which is driving it towards spontaneity, enthalpy or entropy?
Enthalpy.
Enthalpy is driving it towards spontaneity
Right.
because it is a,
Negative number.
but you have to clean. It's not a hot mess.
It's
Hot
a
clean.
yeah.
Dependent upon
Temperature.
low temperature. Okay. So then you get to 3. A sealed vessel contains only carbon monoxide. A small amount of carbon. Reaction occurs and the temperature is held constant. Will the pressure of the reaction vessel increase, decrease, or remain the same?
Decrease.
Why?
Because it's spontaneous.
So what?
So you're changing your 2 moles of gas into 1 mole.
Bingo. So you're going from 2 moles of carbon monoxide into only 1 mole of gaseous reactant. The reaction would be spontaneous. You're going to take some of that carbon out as a gas and change it into a solid. Okay. Oh, that was a lot. Now try the 2017 question 7. Now let me give you a hint before you get too far down into that problem. So you have 2 reactions at the top. Dichromate is a titrant. Titrant just means that's what you're adding to the beaker. Okay? But let me give you a hint. Before you tackle part A and the E0 values, look at how you would have to arrange the half reactions to get to those reactions up above. Okay? So they don't explicitly tell you that, but that's something that you need to think through. All right, Mara, can you stop you on the camera?